The targeted decarbonization of the energy supply and industry requires renewable energy sources such as solar and wind. Since energy must be available regardless of weather conditions, storage and transport, in addition to efficient energy generation, are crucial for the success of the transformation. Hydrogen plays a significant role in this context, as many industrial processes cannot be operated electrically, and it is the only viable alternative to natural gas. Through the construction of a solar park, we aim to convert solar energy into green hydrogen via electrolysis and provide it cost-effectively for regional, international, and global markets. Our solar park will span 3 sites: Bila, Chich, and Golinjevo. These are in the western part of Bosnia and Herzegovina, about 5 to 7 kilometers as the crow flies from the Croatian-Bosnian border. Thanks to the optimal location of the solar fields, they are excellently connected via the PAN, white-marked highways by truck to Mostar and Split airports, as well as to the ports of Split and Ploch. With our project, we aim to achieve the highest possible energy efficiency currently available. That is why we rely on market-ready and innovative technologies at every stage of the process, which surpass conventional solutions in terms of energy, efficiency, practicality, and sustainability. Our project is based on several key pillars. First, renewable electricity is generated in a solar park. Then, the generated power profile is smoothed to balance out fluctuations. Afterward, the electricity is converted into hydrogen via SOEC electrolysis, a high-temperature electrolysis process. This hydrogen is then stored to allow for flexible further use. Finally, hydrogen can be used to produce e-fuels. In the following section, the individual pillars of the project are explained in detail. SOLBUS is building a next-generation solar park at the site. Unlike conventional solar parks, the solar modules used here do not only react to direct sunlight, but to brightness in general. This enables them to generate electricity even during cloudy weather, twilight, and in winter. Compared to traditional modules, they produce twice as much electricity on the same surface area. Additionally, the modules are significantly more robust, which increases their durability and sustainability. Another advantage is that the manufacturing process of the modules is highly efficient. For this reason, they are more cost-effective than conventional modules. Despite increased generation, the solar park's electricity production remains subject to fluctuations between day and night and between summer and winter. To address this, we implement 2 key measures. First, we complement the solar park with innovative battery storage systems based on nanotechnology. These batteries are long-lasting, can be charged and discharged over 200,000 cycles. Moreover, they are lightweight, non-flammable, free from toxins and rare raw materials, making them both sustainable and cost-effective to manufacture. This allows for efficient smoothing of the solar power profile. The second measure involves balancing our own generation and consumption volumes through regional or international electricity markets. This increases grid stability and ensures energy security for hydrogen production. The next pillar describes the method used for hydrogen electrolysis. The smoothed electricity is converted into hydrogen through electrolysis. Traditional technologies such as alkaline or PEM electrolysis are highly energy-intensive and only achieve an efficiency of around 50 to 60%. This means that only about half of the green electricity used is converted into hydrogen. Therefore, SOLBUS relies on commercially available high-temperature electrolysis systems in the project, such as SOEC electrolysis. In combination with the planned hydrogen storage systems, these achieve an efficiency of over 80%. As a result, the amount of hydrogen generated from green electricity increases from approximately 8,000 tons per year to around 13,000 tons per year. This more than compensates for the higher acquisition costs. The hydrogen generated throughout the year must be stored continuously. SOLBUS avoids the use of energy-intensive and expensive compressed gas or liquefied gas storage, which require specialized containers and vehicles. Instead, SOLBUS utilizes the efficient HyCS technology, offering significant advantages. The HyCS technology is based on a well-known chemical cycle in which iron oxide is reduced to iron during charging and reoxidized back to iron oxide during discharging. To ensure that the iron does not disintegrate during this consistent process of rusting and derusting, specially designed iron nuggets have been developed to serve as storage material. Since iron is a solid, a very high storage density is achieved, meaning significantly more hydrogen can be transported than with compressed or liquefied gas storage systems of the same size. At the same time, HyCS storage is not classified as hazardous material. This allows it to be stored almost anywhere, without special permits and transported using existing infrastructure such as trucks, freight trains, and cargo ships. Additional advantages arise from the combination of HyCS storage and electrolysis. Approximately 80% of the electrical energy is converted into green hydrogen via SOEC electrolysis and stored. The hydrogen then passes through a heat exchanger, where it absorbs thermal energy from recycled water. This efficient heat recovery significantly contributes to increasing the overall efficiency to around 80%, as the stored thermal energy of the hydrogen is optimally utilized. Additionally, water consumption in the electrolysis process is significantly reduced, as 90% of the water used remains in the system and is recycled. Before final storage in iron nuggets, the hydrogen is electrically heated to the necessary temperature to ensure optimal conditions for chemical bonding. Storage takes place in the iron nuggets, which allow for safe and efficient transportation. The entire loading process can be completed within 30 minutes. HyCS technology is thus safe, efficient, scalable, and cost-effective, ideal for the hydrogen economy. SOLBUS will produce at least 13,000 tons of green hydrogen annually and store it in mobile HyCS containers equivalent to approximately 20-foot shipping containers. Every day, 40-50 transport containers are filled at 2 to 3 loading stations and delivered via truck to regional customers. Alternatively, transport may occur by rail or ship. At the consumer end, the green hydrogen is fully utilized through mobile or fixed unloading stations. During discharge, 99% of the stored hydrogen remains intact. No H2 is lost through evaporation during storage or transport. Additionally, steam from the user's exhaust is used to reduce discharge costs per kilogram. The H2 to H2 energy balance is 91%, and the overall efficiency after storage is 79%, when exhaust steam is utilized for steam generation. HyCS technology is thus safe, efficient, scalable, and cost-effective, ideal for the hydrogen economy. Finally, we turn to the last pillar of the project. To further expand value creation around hydrogen, SOLBUS plans to establish a facility for the production of e-fuels. E-fuels are synthetically produced liquid fuels made from hydrogen and carbon dioxide. They are carbon-neutral fuels with the same properties as gasoline, diesel, and kerosene. E-fuels enable the decarbonization of sectors such as aviation without requiring modifications to engines or fueling infrastructure, saving both time and costs while reducing dependence on fossil imports. Produced in sun- and wind-rich regions, they can be easily transported. The production of green e-fuels begins with the generation of hydrogen from renewable electricity via electrolysis. In combination with the HyCS storage system, closing the process loop during the charging phase significantly increases efficiency, allowing more hydrogen to be produced from the same amount of electricity. During discharge, hydrogen, steam, and carbon dioxide react to form synthesis gas. The previously increased hydrogen yield results in approximately 25% more synthesis gas. At the same time, the HyCS storage acts as a pressure booster, enabling discharge at the pressure level required for synthesis, even though charging occurs without pressure, because generation, storage, and discharge all take place within a single system. Multiple conventional process steps, such as the use of hydrogen compressors, CO2 conversion, and water treatment and drying near the electrolysis unit, can be eliminated. This significantly reduces both capital and operating costs, increases process efficiency, and strengthens sustainability. SOLBUS is committed to a sustainable energy future by harnessing renewable energy to produce green hydrogen through electrolysis, a climate-friendly alternative to fossil fuels for industry and transportation. The process relies on highly efficient, high-temperature electrolyzers, which increase the hydrogen production efficiency to over 80%. The hydrogen is then safely and efficiently stored and transported using innovative HyCS technology. Power for the entire process is provided by a next-generation solar park, whose modules respond not only to direct sunlight, but also to ambient brightness. This enables them to produce twice as much electricity as conventional modules on the same surface area, even in cloudy conditions, twilight, or winter. At SOLBUS, we see ourselves as pioneers in renewable electricity generation through innovative solar technology and in hydrogen production. We also position ourselves as one of the leading global providers of components for hydrogen transport and storage.